All right. I think that's everything. So it's about time to start class. It's close to 1:35, or I guess it is 1:35. But I'd be happy to answer any questions first about the homework that was just due. I know there were one or two hanging out there, but just please get them in when you can. And I'll assign another homework coming up here that has to do with composites, so you can do some reading on that. But I'd be happy to answer any questions, talk about anything that people want to talk about before we get started with the lecture. Any questions?
I just had a quick question.
Go ahead.
So I remember last class we talked about how sometimes they use a coating and then they apply a microwave, or um, like they send like energy, I guess, to increase the adhesion. Do they ever apply like electric fields or magnetic fields to do a similar type of thing?
I mean, it's possible, but remember, what you need to fuse polymers is time and temperature, right? And so electric fields can generate temperature. I guess magnetic fields could too, but the easiest way to accomplish that interfacial heating is the RF heating or the microwave heating of the nanotubes that are at the interface. And so I think there's lots of possibilities for different material systems, different energy sources. We'll also see some IR heating, so just using high intensity IR lamps and even lasers to do interlayer sintering. And so I think that there's sort of lots of possibilities, but they're all trying to accomplish the same thing, which is to put higher temperature right at the interface to get polymer interdiffusion and to get those layers sintered together. And so however that can be accomplished while creating a strong interface with the right filler, the right polymer, etc., is helpful. And microwaves are interesting because you can buy industrial size microwaves, and so you can put big things in there like cars and other stuff like that. And so it all just depends on what technique you want to use, what energy source you want to use, what materials you want to use. But I think any similar idea is possible. But remember, what you're looking for is polymer chain interdiffusion across the interface. And some of you read some papers on how to get higher chain diffusion, how to put additives in there, perhaps how to cross-link across the interface. And so there's lots of ways that people have tried to accomplish this, and that's just one example.
Okay, thank you.
Good question. Any other questions? Any other points for discussion? Okay, well, let me pull up the slides, and we'll start where we left off, and then we'll introduce a couple of new things this lecture. And we're either going to get to SLS today, or we're going to start with selective layer sintering on Thursday, where we're now, instead of using a heated liquefier to melt the polymer and get it to extrude in rods, we're going to be using a laser in order to induce thermal melting. So it's not photopolymerization or chemistry, it's still a thermally driven process, but there's different things going on besides what we've heard about so far. But this idea of chain interdiffusion in order to make interfaces between solid polymer structures is going to be going to extend when we talk about powder bed fusion. So that's a preview. Let me see if I can get my slides going here. Let's see if I share screen. All right. And the slides. Oh, this comes back. Okay, so we had a couple slides on characterization because I wanted to make sure that everyone was sort of on the same page with what's important about polymer characterization. What did we need to keep an eye on? Of course, if you're really interested in characterization or you know a lot about polymers, you can go deeper and deeper into characterization with different types of mechanical characterization or rheological characterization or imaging. But I wanted to include a couple slides because we've talked about rheology, we've talked about CT, and so as you're reading these papers, you should have an idea of what they're talking about. So this slide deck just gives you a little bit of background on characterization things that you should be interested in. So of course, you can check out the various manufacturers' web pages for what sort of equipment they have. And I think we left off talking about Bingham Plastics or zero flow fluids. And these are interesting because these form the basis for direct ink writing printing. And so we're going to just look at a couple of examples. This one from Jennifer Lewis, because she's published some really nice data of rheology and printing. And so she's really set one of the templates for how you might think about formulating materials for this offshoot of material extrusion AM through direct ink writing. And the only difference between this process and what we've talked about so far in terms of thermoplastic material extrusion AM is these are inks or liquid inks that are extruded out of this nozzle, but because they're self-supporting or because they're Bingham plastics, you can create filaments and you can create three-dimensional structures from these inks. So they don't flow all over the place like we would expect from a Newtonian liquid that can't support a shear stress. So these are sophisticated foams because they're formulated in such a way in order to have this cellular structure. And so there's these larger bubbles, but there's smaller bubbles that self-support this foam. And so this is just really interesting because Professor Lewis talks about how you might formulate one of these materials. And also this is interesting because they report in this paper modulus. So remember G prime and G double prime. Sometimes you see E prime and E double prime are the modulus of various, well, whether it's foams, gels, or fluids in this case. And then the apparent viscosity. So once this is flowing, you can see the shear thinning behavior because as the shear rate goes up, the viscosity goes down. So these are shear thinning. Okay, but you see, but since there is a constant modulus as a function of shear rate until you get to very high shear rate, these are considered Bingham plastics, so they can have this self-supporting behavior. Now, through studying different formulations and looking at different nozzle diameters versus effective print speed, so effective print speed is just how fast the nozzle, in this case, is moving. So that's a linear velocity. And of course, nozzle diameter is just the size of that opening. They've been able to map out areas of clogging, where you're trying to shove too much stuff through the nozzle and it's not working out very well, or the nozzle is too small, so you get clogging of that nozzle. Versus drying, perhaps you're going too slow and you get some drying and break off at the nozzle exit versus a stable printing region. And so there is no quantitative equation for how you develop this phase diagram or this printability diagram, but this happens for lots of different material extrusion AM processes. So how do you balance the speed versus nozzle diameter versus material viscosity properties? etc. So once you start printing in one of these processes, the only way to really figure this out is to construct one of these printability diagrams where you're looking at, say, speed versus nozzle diameter, or at a constant nozzle diameter because you want a certain part, print speed versus viscosity or temperature or something like that. And so as you start to read more AM papers, you'll see these printability diagrams that show the regions of stable printing. And it's, again, it's difficult to predict these diagrams from an engineering point of view, but mapping out the parameter space is often helpful and makes for nice research reports. And then based on these printing foams, you now can get multi-layer structures. So since these foams are self-supporting, you can make lattices, and now you can look at the mechanical properties of foam lattices. So these are dried after they're printed. They're dried for a certain amount of time, and then the mechanical properties are tested. That's interesting, and this gives you an idea of what you can do with this direct ink writing. And they put their results on this plot where if you plot the elastic modulus or some kind of mechanical property versus density, this type of plot is called an Ashby plot or an Ashby type plot. And you see that if you want very strong materials, in essence, you have to go to high density. So 1,000 kilograms per meter cubed or 10,000 kilograms per meter cubed is getting very heavy. But you can get very strong materials. And up here we have technical ceramics. So these are high strength ceramics that they make CMCs out of. So ceramic matrix composites. So this is like silicon carbide and other things like that. Whereas for some of these lattices and bulk foams, so foams that are just extruded without any lattice structure in them, you can approach this parity line right here that really sets the limit for how strong materials can be at a certain density. So you'd like a material to be as strong as possible, but also as light as possible. And there are some real physical limits for how you get really strong materials that are also low density. And so this is one of the things that people have looked at for making these lattices or making lattices out of metals. You see some really nice Ashby plots where people are trying to get closer and closer to what they think the physical limit is for a light and strong material. And the way to do that is to make one of these design lattices. And we'll look at that perhaps as we get further into the semester and talk a little bit about architecture and the interesting things that you can do not only through the intrinsic property of the materials, you're using steel or you're using polyethylene or you're using Ultem, but what can you do with the architecture that gives you some functions that you can't get through the material alone. So that's what these foams are about. And it's just a nice demonstration of all the different sorts of parameters that you can bring together. Any questions so far? Any comments people have? Okay, I'm keeping an eye on the chat box in case anyone has questions, so just chime in there or go ahead and unmute yourself and stop me as needed. So along the lines of this direct ink writing, there's this really interesting example of bath printing or in-gel printing or embedded printing, where now you have a supporting bath, and you have some sort of neutral density liquid or a liquid that can be sequestered in that bath. So this is a printing ink. And it's basically injected into this bath, and you can see from these diagrams that they're able to print this hydrogel material in some sort of supporting bath. And that supporting bath can be a liquid, it can be another hydrogel, it can be a polymer solution. There's lots of different variations of this, and we'll look at a couple of really interesting examples. But this idea of embedded printing can give you some really interesting functions. And so this is another example from the Lewis group, where now they're printing conductive traces. So this is conductive in PDMS. And so this is really interesting because now you can get different functions for your ink material. So you see an ink, this will be a road right here. This is our nozzle. And to make this work, they needed a fluid on top of this to allow some fluidization of the printing. But this is really interesting because now you can, in essence, print these inks inside another material. So rather than having a layered structure and having to print one layer, then the next layer, then the next layer, you can print inside this gel material, and then of course you can cure the PDMS and you have a solid sample, and we'll see a demonstration of those in a second. And so again, they report the viscosity and the modulus of the ink and the reservoir and the filler fluid. The exact numbers are not really important, but this is just characterizing the materials and demonstrating that they know how this is working in terms of the printing. And then they demonstrated some really interesting strain sensors. So these are strain or printed strain sensors in elastic matrix. So these strain sensors basically change resistance. So this is change in resistance. And so as the hand has different shapes here, you get different different changes in resistance of the strain sensors. And so that's some signal, some kind of signal that you can calibrate to pick up movement of these strain sensors. And so this is now where we get into both multi-material functional printing. And so it's multi-material because it's a number of materials integrated together to achieve some sort of function. And of course, we're printing this all up. And so this, in essence, is a type of composite. And so that's very interesting because some of the things that we've talked about in terms of what is the interface, is there any failure at the interface between the two materials? How do you integrate these two materials together? Now, this is not a homogeneous composite like we've talked about commonly, but there's still some of those issues of how do you integrate those two materials together. And of course, if you're interested in lots of different materials, they've published this thing, which is, I think they called it the Octobot. And so you could take a look at what people are interested in where they have a soft robot. So this thing is all PDMS, which is a type of silicone. and then they're able to print functions into that structure. So you can read that paper if you're interested in soft robotics. I think 3D printing of PDMS has really advanced this field. There's all sorts of cool stuff out there in soft robots, and 3D printing has really helped that along. So here are the videos if you want to see those. We won't watch those this time, but it's something to think about. Okay, so wrapping up characterization. So that was about rheology and the interesting things that you can do with rheology and mechanical properties. But wrapping up characterization, we will wind up with imaging. And so imaging is good. It's how we get some information on the physical form of the part. But I put this comment here: what's wrong with this micrograph? Of course, it doesn't have a scale bar. So we'll have to read the paper to figure out what it is. And also, we can see observed defects from printing. And so whether this is a optical micrograph. So when it says photograph of microscopic cross section, this is an optical micrograph. So you take it on a high magnification camera or on a microscope, and you can see the reflectivity, tells you where the gaps are. But anyway, this allows you to start to characterize either the cross-section of 3D printed parts or the surface features of 3D printed parts. And of course, there are measurements of roughness. There are measurements of tolerance and dimensions. But this is how we start off making some scientific observations of what's inside these parts. So if you've ever taken a metallography course, because this is material science, and so you can learn all about metallography cross sections. You embed, you cut, and you polish. So this is an embedded sample being polished. So if you look on this optical micrograph, you see these striations. So these are usually from polishing. So that's a signature that this cross section was polished flat, so you can get a really good in focus optical micrograph from that. And it's done on one of these things. And so if you walk by the first floor of Steidl building, you'll see the polishing lab, and we have a couple of these in there. The other way to get dimensional measurements on 3D printed samples is called X-ray CT, or CT scanning, or X-ray computed tomography, where now you have an X-ray generator. So this is called the source. This is a detector, or this could be a CCD or something like that. And so in this measurement, all you do is rotate the sample through this X-ray beam and take a couple pictures. Oh, hold on. Paula, I wasn't looking at the chat. I'm sorry. How is the ink not combining with the fluid inside? So let me go back. When you do this ink printing, that's a good question. So because these inks and the reservoir, so you're printing the ink in the reservoir, these are both Bingham plastics, which means they don't flow under zero shear conditions. So when you have a Bingham Plastic, you can do this sort of self-supported printing. If we tried this with like oil and water, we wouldn't get the same result because, of course, water, it, you know, can't support any shear stress, right? Because water is a Newtonian fluid or a Newtonian liquid, and so it flows right away when it's under stress. So the only way that you can do this embedded printing is if you have two Bingham plastics and you're printing one inside the other, because they'll stay they'll stay together as a fluid and they won't float around, other than if subject to high shear. Because of course Bingham plastics will eventually flow when you shear them, but they'll sort of stay in place if you're not actively shearing them, like peanut butter, like cake frosting, right? You can make a structure in cake frosting and it'll just sit there unless you push on it too hard, and of course then it will move. And so the same thing is happening here, is that when you have two Bingham plastics, or you have two zero shear fluids, you can print one inside the other and they won't float around. Now you might get some molecular diffusion right at the interface, so you might get some smearing, but that's on a very small length scale. You can still get good resolution through this technique. So that will only happen if you have two non-Newtonian fluids. Does that make sense?
Yeah, that makes sense. Thank you.
Yeah. Okay. So you can't do this with like oil and water. It won't work. So you need two non-Newtonian fluids, and they tend to have to be strong Bingham plastics, so they won't flow as you're shearing and printing. Okay.
Right.
Good.
Okay. Thanks.
Good question. Okay. So back to X-ray CT. So this is really interesting. If you've ever seen an X-ray CT, that sometimes the source and detector move around the object and the object is stationary, or sometimes the object rotates and the source and detector are stationary. So if you've ever gone to the hospital and had to have a CAT scan, whoops. Let me back up here. So a CAT scan is computer-aided tomography. And so in a CAT scanner, they put you inside this magnet, and the magnet and detector rotate around you, and you're just lying there because, of course, they don't like to rotate people in the hospital. But we have CT scanning on campus at University Park. And so there it's a big X-ray generator and X-ray detector, and you put your part between the two, and then you rotate it around and you take pictures at all different angles. So you take many X-ray radiographs. I can spell here. As object turns. So you might take 800 images, or you might take an image every quarter degree of an angle or something like that. So it depends how long it takes to acquire that radiograph. It depends on how long you can wait. Depends on the stability of the system, because you'd all like all the radiographs under very similar conditions. But you take a bunch of pictures, or as we say in X-ray, radiographs as a function of angle, and then you can reassemble all of those two-dimensional images, which is what a radiograph is, into a three-dimensional model in X, Y, and Z. And that math won the Nobel Prize in Physiology or Medicine in 1979, because they came up with the mathematics that allowed to go from many 2D images to 3D model. And so that's called tomography in general. And of course, you need a computer to do all the math because you can't really do tomography by hand. So computer-assisted tomography was a real breakthrough, of course, in medicine because you could see inside a body in 3 dimensions. And now we use it for all sorts of things, like at SIMP 3D at Penn State. We have this GE CAT scanner or this CT scanner where you can put metal parts inside and you can see the inside of additively manufactured parts or any 3-dimensional part. So you can look for flaws, you can look for internal cavities, you can get accuracy of your process, tolerances, all those things. And so this is really interesting because you might put something like an engine block or this very little engine block inside your CAT scanner, and you have the X-ray source here. You have your X-ray detector. So you're taking many 2D images as a function of part rotation angle. And then you take all those 2D images and with the help of a computer program, you reassemble them into a digital 3-dimensional model. So just like you start 3D printing with a digital 3-dimensional model of whatever sort of thing you want to build, you can compare now 2 digital models. So you have the real digital model from CT scanning, and then you have the part that you wanted to make from your CAD drawing or something like that. And so now you can see inside the sample. So in this FDM sample, you can slice the object whichever way you want. So this is slicing in the XY plane here. And this is slicing in, I think this is the YZ plane right here. And you can look at different cross sections. So you can look at these different digital cross sections, and if you have this well calibrated, you can get dimensions, flaws, etc. So you can look inside your part without cutting it open. Because of course, in order to get a micrograph like this, you have to slice your part, embed it, polish it, etc. So you have a destructive test. So we might call this a non-destructive test, as long as our sample is not activated by X-ray radiation or degraded by X-ray radiation in any way. We might call this a non-destructive test so we can get tolerances, dimensions, just like I said. We can compare to designed CAD model to see if what we wanted to print was actually what we printed. And so that's covered in other 3D printing classes in the AMD program. And so we won't talk much about that, but printing fidelity, or what we might call a digital twin, where you have a 3-dimensional CAD model of the part you want to build, you build it, and then you scan that physical part and get a second digital model, and you can compare the design digital model versus a real digital model, and you could say, oh, my printing process was working here, it wasn't working here, you know, this is not quite right, I didn't plan on having a flaw here or a gap here. And so there's lots of interesting analytical analysis, or there's lots of interesting analysis that you can do to try and figure out how well your process is working. Okay, So that is just a quick overview of characterization. I wanted to make sure you had some vocab words. Of course, if you're interested in specifics about certain types of characterization, you can dive deeper into that as we move on in our homework and our reading. But I wanted to make sure that we had some baseline for discussion. So any questions, anything that people want to bring up or talk about in this set of slides? Okay, I don't hear anything, and so I'll keep an eye on the chat in case something occurs to you. But let's switch over then from lecture 5, and we're going to finish up material extrusion AM. Oh, let's see if I can find my slides here. Oh, bear with me for a sec while I pull them up. We're going to finish up material extrusion AM just with a very quick couple slides on design of parts. And so there's a lot of design guides out there. It depends on exactly what you want to make. And there's a lot of guidance that's more rules of thumb than analytical guidance, but at least this gives you some idea of what to think about when designing parts and what's possible. So again, we're trying to build a part out of filaments, and so you're trying to make a solid engineering part with our fundamental units that look like this. And of course, the fundamental unit that we're going to print with is different depending on the 3D printing process, but this is what we have for material extrusion AM. And of course, there's lots of industrial printers out there for material extrusion AM, and you've seen this before. We've seen this before, and so there's production grade parts being made. And I think when we talk about uses in automotive, you'll see a couple other examples of material extrusion AM. But this is, you know, even though we talk a lot about MakerBot printing or Ultimaker printing on the small scale, you know, this is a serious 3D printing endeavor that people are using to do industrial scale parts and prototyping right now. So it's not just MakerBots. You know, this Fortis 900 MC is a serious machine, and they're doing serious things with it. So we've seen this before, and 3D Hubs actually has some pretty good case studies and some pretty good knowledge bases on different types of processes. And this is just one on what they call FDM, but you know that FDM is material extrusion AM in ASTM nomenclature. But you can see that the typical layer thickness is on the order of 0.18 to 0.5 millimeters or even more. Minimum wall thicknesses are 1 millimeter. And so these are big dimensions. I mean, you're not looking for very fine jewelry or high resolution parts. This is an order of magnitude worse than any sort of CNC machining or something that you would do. And so you're really looking at low resolution parts out of common thermoplastics. Either sort of low strength or higher strength thermoplastics, and you can have support material and other things like that. And so these are some rules of thumb that it's going to be hard to get tolerances better than 1 millimeter. And so you're going to be stuck with prototype parts and things where you can really see the signatures of material extrusion AM based on the road extrusion. And of course, you could increase the resolution of the part by decreasing the size of the road, but you get to a very small nozzle diameter. And so with small nozzle diameters, your pressures go way up, you have clogging issues, and it's going to take forever to print that part because you're only printing a certain linear distance of roads per second or per hour or something like that. So as you go to smaller and smaller nozzle diameters, you basically are extruding less material as a function of time, which gives you a smaller and smaller part. And so there are some real limits to what's practically achievable with this technology, even though people would like to have 50 micron diameter nozzles or 10 micron diameter nozzles. It's just really hard to extrude thermoplastics out of that. And so again, this is from 3D Hubs, and there's some guidance on how you might design these material extrusion AM parts. And here they're just demonstrating a bunch of different sorts of parts that can be printed with this technology. And we'll walk through just a couple different phenomena. So when we talk about this in future lectures, you know what bridging is, you know what overhang is, etc. So we'll define a couple terms as we just walk through a couple slides from this. And you're welcome to read the whole guide if you want. There's other ones as well from Stratasys or whomever else, but this gives us a basis for discussion. And so bridging is just like it sounds. So you have supports on each side, here and here. And so how far can you bridge across an unsupported span? And so that's interesting because that requires good melt strength of your polymer. It also requires the polymer to have a relatively high modulus as it's cooling quickly. And so bridging is not easy with some of these thermoplastics, especially if they flow too much or if they want to flow too much. And so you need to get the temperatures just right, or you need to use supports. And so we talked about PVA as a water-soluble support. And we saw that video from Ultimaker, or you can use supports of the same material and have them attached just with a very small contact area. And I think another class in AMD covers the philosophy of supports and how you might put them in to your model. Of course, there's computer programs to help you with that. But this idea of bridging where you can't extrude material across too far of an open span is something that you need to keep in mind for thinking about how your 3D printing process relates to the physical shape that you want. If we're interested in making holes or vertical holes where we're now making a hole with layers, so this is layers of roads here, and we're going to have a hole. So this is layer So you see for this vertical axis hole, you're going to get some road compression. Of course, you want to extrude nice round filaments on the cross section, but that hardly ever happens because you need some compression to get things to stick together. And so you see the hole is going to be deformed on the edges, and the hole is going to be smaller than you plan. So the computer thinks that the hole is going to be this big based on the road size and where it's putting the roads, but in actuality, you have some difference between the actual diameter and the slicer diameter, and the slicer diameter is just from software. So remember, you have a CAD 3D model, and that's sliced to get different two-dimensional layers, and then you print it. And the other AMD classes will talk about that exact workflow, but if you read up on how you go from a CAD model to a 3D printed part, you can get the gist of what's involved. But suffice to say that the hole size that you plan for is not the hole size that you're going to get in FDM because of this road deformation and this compression. So that's something that you have to watch out for. Also, overhangs, just like bridging, is an issue. And so this is a panel of overhang bars. And so they have the angle printed in right here. And so that's cool because this is a nice test, and eventually you get to poor overhang performance because this polymer can't stick together at that steep angle. So this is on the way to bridging, but this shows us what's possible in terms of designing an FDM part. And if you have experience with 3D printing, this is pretty elementary stuff, but it's important to be familiar with some of this nomenclature. So people who are learning 3D printing for the first time or thinking more about 3D printing for their research now have some technical terms and some vocabulary in order to communicate the issues they're interested in. Oh, I see a question. I'd assume there's not a predict the size of the hole you actually get. Yeah, so, okay, so Brianna's question, everyone can see it here in the chat if you bring up your chat box. So Brianna says, I would assume there's not a way to predict the size of the hole you will actually get. Is it typically a range, or will it really just depend on the print and all the settings, including the material type? So it depends is really what it boils down to, because what it depends on is how much compression do you get versus how asymmetric the road is versus how wide is the hole to begin with. So if you want to make a 2-inch hole and you get, say, 20 microns of compression, that's not a big deal because the hole size is very big compared to the deformation. But if you want to make a 1 millimeter hole, or if you want to make a 5 millimeter hole, and you're getting 0.5 millimeter of compression, that can cause a big difference. And so it really depends on how much compression you get, depends on the flow properties of the polymer, and of course it depends on the details of the part in terms of the nozzle size versus the hole size, etc. And so, you know, eventually if you print a bunch of different size holes, and I think in one of these, they don't have a bunch of different size holes printed, but there are test pieces where you can print a bunch of different size holes, and you can get this idea, or you can get this information between planned size and real printed size to help you say, okay, these are my limits for how I make holes. So for a lot of this stuff, and even for overhangs, depending on the material and depending on the temperature and the printer and the print speed, you know, whether you can get a 60-degree overhang or a 70-degree overhang or a 45-degree overhang, you know, this says overhangs can usually be printed effectively at 45 degrees, but to go above 45 degrees, really, there might be issues. But it depends on the polymer in the process. And so all of these things, whether it's bridging or hole deformation or overhangs, just really depends on the system. But these are some things that you might want to characterize if you're trying to characterize the printing characteristics of a material or the printing characteristics of a certain process. These are the types of things that you want to ensure that you can print, so you know what the limits of the printing process are, and you can communicate that to the designers when they're thinking about a part. Does that work?
Yes, thanks.
Great. And so the last thing, or one of the other interesting things in this article that they discussed, was this idea of the build direction, or what direction do you want the layers oriented in comparison to the load. So if you're familiar with 3-point bending, this is a 3-point bend. It's a general geometry of a mechanical characterization test. But if you have poor interlayer adhesion, this part is going to crack at these interfaces because in general, parts are not as strong between layers of roads versus if you're going with roads across the loaded direction. So this is a continuously printed road. And so the part will be strong in that direction versus the part will be weak if we're loading it across the roads like this. Same thing in tension. So again, you have lots of interlayer adhesion issues in this part. And so if you try and pull across the roads, it's going to be weak. But if you pull it on the road or pull it in the direction of the roads, it's going to be stronger. And so, of course, this gets to the idea of anisotropy. Due to road extrusion direction and road adhesion. And now we usually talk about road adhesion in terms of interlayer adhesion. So this is layer 1, and this is layer 2. Of course, we're going up. We would call this interface right here interlayer adhesion. And so that's often the weak part in a material extrusion AM part because the layers take a long time to print. Because of course, as you're printing a 3D part, you print all of layer 1 first, then you print all of layer 1 second, then all of you print all of layer 1 first, you print all of layer 2 second, all of layer 3 third, et cetera, et cetera. And so those layers cool off a lot between printing. And so that's why the interlayer adhesion is generally weak. Now you also have road to road adhesion. But these are usually printed together in time a lot sooner. So depending on how big the part is, of course, and how long it takes the printer to trace the object, road-to-road adhesion can be an issue, but that's generally not as bad as interlayer adhesion. So interlayer adhesion is usually much worse than road to road adhesion. So that's just something to think about, and that's what this diagram is trying to point out. These are all interlayer adhesion issues rather than road to road adhesion issues, even though you know building a three-dimensional part is going to take many roads per layer. So that's something to remember, and this is something that you can see as you print parts. If you have really weak interlayer adhesion, sometimes you can break these parts or you can peel off the layers, or if your temperature of your heated liquefier is too low, the layers don't stick together in the first place. And so, well, you can qualitatively assess this idea of anisotropy and interlayer adhesion. The build direction could make a big difference, especially if you're producing an industrial part. So if you try and print these parts in a different orientation, they're going to perform differently because their mechanical properties will be different depending on the direction. And of course, printing these things that are round in the YZ is going to be difficult because you're not going to be able to get perfectly round parts because you're going to have some sort of collapse. And so printing round things in the XY is probably the way to go, even though you have some vertical hole offset due to compression. So this was a quick guide for thinking about, okay, how do I make parts out of FDM? What do I do if I want to make a part or have different anisotropy or different build orientations or different mechanical properties? And so generally, the materials people and the mechanical engineers and the 3D printing technicians will all get together and figure out, depending on people's skills, what's the best way to make these parts. So that's just a quick overview to give you some basis if you've never thought a lot about 3D printing. If you're interested in more details of 3D printing software or build orientation or other sorts of engineering aspects of additive manufacturing that aren't materials, there's a lot of different courses on campus. Of course, this course is focused more on materials, so we'll get back to materials and processes in a second, but I wanted to make sure that we're all on the same page with regards to some of the basic issues. Any questions or any points for discussion here? All right, I assume that everyone's studying their 3D printing and watching the YouTube videos and other things like that to get more familiar with the physical processes of 3D printing, but if you need some more guidance, let me know. So that ends material extrusion AM in terms of what we're going to talk about in class. So if you want to hear more about material extrusion AM, you can ask me questions on the discussion section on Canvas, or we can talk more about different materials that are extruded or different parts that are built using material extrusion AM. We'll see a little bit when we talk about aerospace and automotive applications in a focused manner, but those are the basics that I wanted to get across from material extrusion AM. And now it's time to turn our attention to another thermal processing technique. So this is still thermal processing, but we're gonna do thermal processing using SLS. So SLS stands for selective laser sintering, or this is also called powder bed fusion. And for that, we need a laser and we need polymer powder. So even though that this is a thermal processing technique, it's completely different than what we've studied so far with material extrusion AM. How we melt the polymer or how we soften the polymer is different. We're going to use a different energy source, and the feedstock is completely different. We're going to use a powder versus using a filament or a pellet. And so we go back to our ISO ASTM standard terminology for additive manufacturing. And so we're dealing with polymers. We're dealing with thermal. We're dealing with powdered material. We're going to have a powder bed. And we're going to do selective fusion. And so the ASTM designation for this process is called powder bed fusion. So some of you might have seen powder bed fusion processes for metals, and we'll discuss the difference between powder and metals, but we'll get oriented in this lecture to what's going on with powder bed fusion of polymers. Any questions so far? Any discussion points that people want to bring up? All right. I don't know if anyone has seen or if anyone has any experience with powder bed fusion, but you can raise your hand using the buttons on Zoom, or you can give me a thumbs up or something if you have any hands-on experience with powder bed fusion in something like this. So does anyone out there have any experience with powder bed fusion of polymers or metals or something like that? Good. Not many others. I know Kenny and Locke have seen a little bit of powder bed fusion in their lab, but powder bed fusion is a lot less common than material extrusion AM because the powders are difficult, they're more expensive, they're more dangerous to handle. You see this person has a respirator on, and this is in a glove box. This is polymer powder. And the machines are much more expensive because they need to move this laser around, and that's just a more expensive technology than moving a heated liquefier around with the XYZ motor. So we'll watch a couple of these videos next time. My favorite 3D printing video is a powder bed fusion video, so I'll show you that in a second. But I want to talk about the mechanics of the process first, and so we all know exactly what's going on when we're talking about different parts of the printer. So we have this thing called a powder bed, and so that's where the build is going to take place. So here's the laser, and this laser is a long wavelength laser to induce thermal heating of the powdered material. And of course, if you heat up powder, you know that you can sinter that powder, you can stick that powder together. And we're going to talk about the physics of what that is. And so how this works is that you have a powder roller or powder spreader. And so this is going to make your layers. So this is one layer at a time. And so you spread a layer of powder, then you draw your object in it with the laser, and you steer the laser with this thing called a galvanometer, which basically controls where the laser hits the surface of the powder bed. And then the build platform goes down, the powder roller rolls on another layer of fresh powder, and you start again, you write your layer in there. And we'll watch some YouTube videos of what this is, but this is, again, a layer by layer additive build process where now you're sintering powder together to create a three-dimensional part. And that three-dimensional part is sitting in the powder bed. And so we'll see some videos of that. It's really cool because this whole powder bed comes out as a big cake of powder, and then you have to get rid of all the loose powder to find your three-dimensional part. So it's like a sandbox treasure hunt or something like that, if you've ever seen that. Okay, this is just another diagram of exactly the same thing. So here's our XY scanning mirror, also called a galvanometer. Here's the long wavelength laser with some lenses in order to get the right beam shape. You have your sintered part embedded in the powder bed. And in this diagram, you have two powder feed reservoirs because now your roller will roll one direction, the part will be written, and then the roller will roll the other direction, the part will be written. And so this can increase or give you faster build speed because the roller doesn't have to go back and forth across the part. So it turns out that powder spreading can take significant time. And so that will add to the build time of your part. And so there's a rest period where you're doing powder spreading where you're not building anything. So the build times can be long. Of course, laser spot sizes are not very big, and the laser has to trace the entire solidified part that you want. So just like FDM, you have to go voxel by voxel to sinter the material together or to deposit the material, but then you have to wait for the powder to be spread as well. And so if you're interested in the details of powder bed fusion, you can read up in terms of what the duty cycle is, or how much powder spreading time do you need versus how much part writing time. And it can be considerable depending on the details of your process. But this is to help you get oriented in terms of the physics of what the process is. And we're going to talk about how the polymer plays its role in this powder bed fusion process. And one of the things that polymers don't do very well is polymers melt, but they don't melt to low viscosity liquids. And so if you look at the viscosity of molten metals, so this is the viscosity eta in centipoise, you see that as you increase the temperature of molten iron here, the range of viscosities is, this is a decimal. So this is 12.0, this is 16.0, this is 4.0. They have very low viscosities. I think I see this decimal right here. But if you look at polymers now, so as you change the molecular weight, you have viscosity in centipoise of 10, 100, 1000, etc. And we've talked about the critical molecular weight, where as you increase the molecular weight, you get this change in the scaling of the viscosity with molecular weight. But now polymer melts have viscosities that are hundreds of centipoise, whereas molten metal has viscosity, liquid metal has viscosity of tens of centipoise. So liquid metal tens of centipoise, whereas let's call it, well, I'm going to call it polymer melts. Hundreds of centipoise. And a centipoise is just a measure of the viscosity. And so a molten polymer is much more viscous than a molten metal, which means that it's much harder to fuse polymers together than it is to fuse metals together. And so if you've ever seen an SLS or an SLM, so selective layer melting is sometimes used for metals because the metal is actually a liquid at this laser beam right here. So right here you have the sintering or the melting. So when you do SLS of steel, you have a melt pool right at that laser spot, and that causes fusion of the metal powder. Of course, it's easy to fuse things together if they're low viscosity liquids. But fusing polymers together is a whole other matter because it takes a lot more time, and the fusion is very slow when you have a high viscosity melt. And so there's some things that we have to consider in order to fuse polymer powder together, whereas it's much higher temperature to do selective layer melting or SLS of metal, but that fusion can happen much faster. So if you're interested in additive of metals, Professor Allison Beasy teaches a really nice class in the AMD sequence on additive manufacturing of metals. But I wanted to bring this up of metals versus polymers because the physics of fusion is different between the two materials, and these are both production technologies, even though SLS or SLM of metals is much more widely practiced. than SLS of polymers, it's important to note the similarities and differences. Are there any questions about this so far? All right, couple more slides. So we've talked a lot about rheology, and so remember, we need to know what the rheology is of the material when it's melted, and we get that from one of these plots right here. And because polymers are zero shear fluids, or they're Bingham plastics, you know, if we just have a powder bed sitting there or a piece of powder sitting there and we hit it with a laser beam, even though it softens, it needs to soften a lot in order to flow. And so we need large drop in viscosity at high temp to get powder to fuse. So we're not making a polymer liquid like we are making a molten metal droplet or something like that. We need to get the polymer powder to sort of fuse together under this zero shear condition. And so we can characterize that through rheology, and we'll talk a little bit about that and the different types of flow rheology that we might need. So I'm just going to end on this last slide as you think about polymer powders, and we'll come back in a second to the previous slide or next time. Polymer powders are dangerous because they're so light. And so metal powders are dangerous as well because they're high surface area metals. And so there's issues with breathing metal powders and other things like that. But polymer powders are exceptionally dangerous because there's a lot of dust and they stay up in the air for a very long time. So if you have any sort of ignition source and you spray powder into that, or if you take cornstarch or something like that, there's these grain elevator explosions. That's grain dust, but of course dust from grain is just like organic polymer powder. And so my message is that polymer powder safety is really important, and that's why people wear respirators when they do SLS of polymers. That's why the video that we'll start off with next time, you see them doing this process in a clean room. That's why this is in a fume hood. For powder containment. And so polymer powders are dangerous materials, and we'll talk more about the size of polymer powder. We'll talk about how polymer powders fuse together. We'll talk a little bit more about machines and what's possible in terms of the different types of polymers, and we'll compare and contrast powder bed fusion to material extrusion AM as we start to build up our knowledge about polymers and composites in AM in general. Okay, are there any last questions? I think we'll end right here and we'll kick it off next time with a big discussion of SLS and processing powdered polymers. Is there anything, any discussion points people want to bring up or any questions they have before we close today? Okay, well, that's all I have for you. And so I will start going on another homework. You'll see that pop up. And please ask any questions that you have by email. I'm available for office hours. And we'll keep going. And we'll start this new unit on SLS of polymer powders, or we'll continue this new unit of SLS of polymer powders next time. Thank you very much.
Thank you.
Thank you.
Thank you.